Dear students, in the previous lecture, I discussed about the interaction of heavy charged particles with matter. And we found that the important properties of the heavy charged particles with regard to their interaction are the stopping power. The stopping power is nothing but the loss of energy in the unit thickness minus dE by dx. And we also saw how that is related to the energy and charge of the ion. So there is a term depending upon the property of the ion. There is another term depending upon the property of the absorbed medium, that is NZ, electron density, number of atoms per cc into the atomic number of the material. So it is essentially the electrons per cc. So heavy charged particles are losing energy relatively much faster because they don't travel much because of the higher mass, higher charge. So mz squared by E, as you recall the previous lecture, the energy, as the energy decreases, the stopping power increases. But as the Bragg curve signifies, at the end of the journey, finally the velocity of the ion becomes less than velocity of electrons, and the heavy charged particle picks up electrons and then stops. At the end of this track or the range, the stopping will be purely by the nuclear. But in the beginning, it is electronic stopping, wherein the ionization and excitation are the dominant mode of interaction. Now we will discuss the interaction of fast electrons with the matter, which also includes the beta particles, beta plus and beta minus. Okay, so the fast electrons or beta particles, the interaction mechanisms are same. Even positrons will behave the same way. And the typical energies of these fast electrons or beta particles that we handle are in the range of few keV to few MeV. Now, this in terms of the type of mechanism for interaction of these fast electrons with the matter, we can say that there are two types of processes that occur. First is the collisional energy loss. That means the electrons collide with the electrons of the medium through which they are passing, and they can cause the ionization and excitation, very much like in the case of heavy charged particles. But in addition to this, there is another mode of loss of energy, and that is the through radiative energy loss, in which case a continuous radiation called Bremsstrahlung is emitted when the fast electrons are passing through the medium. We will discuss more on this subsequently. The major differences between the interaction of heavy charged particles with fast electrons, let us discuss this first. So firstly, the velocity of electrons is much higher than the velocity of heavy charged particles for the same energy, let us say few keV to few MeV. So because of that, these velocities are very high. The delta E by dx, the stopping power for fast electrons, is much lower than that for the heavy charged particles. If you recall the stopping power formula, dE by dx is equal to mz squared by E. In fact, it will not remain the same when it comes to electrons, but the velocity comes in the denominator, and so velocity is high. That means the stopping power is low, grossly speaking. The second important point is that the energy transferred by electron to the electron in the medium in one collision. So considering the same equation in case of heavy charged particle, the maximum energy an electron can gain when it is struck by the incident particle, maybe alpha or electron, given by 4mm, capital M small m, E0 upon m plus m square, cos theta. In fact, it's cos theta, theta equal to 0. Maximum energy is lost when theta equal to 0. Now, if you substitute for capital M as mass of the electron, so both capital M and small m are same in the case of electron interaction. And so this will become E max equal to 4m square E0 upon m plus m is 2m into square 4m square. So it will be E0. That means the electron can lose all its energy in single collision when it is colliding with an electron. Because of these processes, you will find that the electron can get scattered in all angles in a single collision. So this is a major difference when it comes to interaction of electrons with matter vis-a-vis the fast heavy charged particles. The third difference is that the electrons move in a tortuous path. The reason for that is the second point, that is the electron can lose energy in a single collision. And so because of that, suppose you have an electron here, it is colliding with another electron. This electron can get scattered in different directions. And so because of that, when the electron is going, it is scattered, it can further get scattered. Whenever it is interacting with an electron, it can go. So this electron can go in a zigzag path, and so you can say the different electrons will be moving in the tortuous path, like a tortoise in a zigzag fashion. So you cannot define a well-defined range for the electrons because their motion is tortuous. That is because of the large energy transferred in single collision in case of fast electrons. Another major difference is that when the electrons are interacting with the medium, particularly at energies which are of the relativistic order, there is an emission of a continuous gamma radiation, the Bremsstrahlung. That Bremsstrahlung is derived from the word breaking radiation. That means when the electron is accelerated or decelerated in the vicinity of a nucleus, because of this electromagnetic interaction, the electron loses energy in the form of photons. So that can be explained from electromagnetic theory. And this happens when the energy of electron is of the order of relativistic energy. That means beta equal to V by C, V the velocity of electron, C the speed of light. And when it is close to 1, then the electron is relativistic. And so that happens for electron when the energy is of the order of 1 MeV. And therefore, the MeV order of energy electrons will undergo a large fraction of energy will be lost through Bremsstrahlung radiation. The same thing doesn't happen in case of protons of same energy, because for 1 MeV proton, the beta value will be around 0.046, which is much less than 1. Therefore, proton is not relativistic at energy of 1 MeV. The result of that, you don't see Bremsstrahlung in the case of heavy charged particles at these energies. High energy it may be possible. We'll discuss that later on subsequently. So let us first discuss the collisional energy loss and radiative energy loss with regard to the stopping power. So we will not go into details of the derivation of this formula because they are quite complicated, but hence Bethe in fact derived this formulae. And so here, instead of one type of collisional stopping power, we have two types of losses. One is the loss in a collision with electrons, so they call it collisional energy loss. And this collisional energy loss again has the two terms, the electronic properties, the ion, single ion that is impinging, 2 pi e to the power 4 upon m0 v square, where v is the velocity of electron and mz is the electron density in the medium. And this is term again the velocity dependent is a relativistic term. In the case of beta particles and fast electrons, relativistic term becomes important because beta is significant, close to 1. But let's not go into too much details of the relativistic term. It simply is sufficient to say that in the collisional energy losses again depend upon the velocity of the electron and the electron density of the medium, in the fashion similar to that of the heavy charged particles. And the radiative energy loss, they call radiative minus d by dx r, is again given in terms of the electron atom density. So mz is nothing but electron density, E is the energy of the ion, e to the power 4 upon 137 m0 square c to the power 4, and some term depending upon En m0 c square. So electron is going to lose energy not only by collision with electrons, which leads to ionization and excitation, but also by loss in terms of emission of electromagnetic radiation, that is Bremsstrahlung. And so the total energy loss now by the electron is sum of the collisional energy loss plus the radiative energy loss. And for the higher energy electrons, and particularly, if it is going to stop in a high Z medium, then the radiative losses become very, very significant. Just to give you the feel of that, the dominant role of radiative energy losses, the ratio of radiative to collisional energy loss. So this upon this, radiative upon collisional losses. If you see these two terms, in the simple way, it can be written as Ez upon 700. We will not bother about the terms, how it has been arrived, but E is the energy in MeV, Z is the atomic number of the absorber upon 700. So it's a very simplified way of finding out the ratio of radiative to collisional energy losses. So what it tells is that higher is the energy of the ion, higher is the radiative energy loss, higher is the Z of the absorbing material, IZ materials, higher is the radiative energy loss. So if you are having a high Z material in the vicinity of a beta emitter, then you will have more of radiations. So that's why you handle beta sources, you have to be very careful about the nearby high energy material, high Z materials. So for beta particles of the order of 1 to 2 MeV, in fact, radiative energy losses are not that high. But if it is a high absorber, high Z material, then the radiative losses become significant for beta particles of this energy domain. So when you do beta counting, the absorber, the plate on which you make the source becomes important. You should not make the source on a high Z backing material. You can make on aluminum, not on stainless steel or any other high Z material. So let's now discuss more the Brimstollen. The Brimstollen, as I mentioned, it derives from the name braking radiation. That means suppose you apply a brake. So when you apply a brake on electron, this electron is losing energy. So how does it lose energy? Say if it is going in the vicinity of a nucleus, and nucleus has got charged particles like protons. So electron can be accelerated in the vicinity of the nucleus, or it can be decelerated. Then any accelerating or decelerating particle, charged particle, loses energy by means of emission of electromagnetic radiation. So essentially, in the electric field of the nucleus, if the electron is accelerating or decelerating, then it will emit a electromagnetic radiation. And this electromagnetic radiation is, in fact, in the case of electrons, it is 10 power 6 times more for electrons than that for protons. So why it is so that we did not have the Brimstollen type of radiation in the case of protons and alpha particles? So the explanation lies here. That is the force, the Coulombic force between the electron and the nucleus. You can say mass into acceleration, mass m into a. So the acceleration is F upon m, and the Brimstollen intensity is proportional to square of acceleration. So acceleration square. So if you assume that other things are constant, then it is 1 by m square. So the Brimstollen intensity is proportional to 1 by m square, where m is the mass of the accelerating ion. So now based on this, you can say the intensity of Brimstollen for electron divided by electric intensity of Brimstollen for protons can be in terms of inverse ratio of their masses. That is the mass of the proton square upon mass of electron square. And the mass of proton to mass of electron is about 2000, and square of that is of the order of million times. So that explains the Brimstollen intensity for fast electrons a million times more than that for the proton. So that as a result of that, you will find we don't have Brimstollen for protons and other particles of energies of few MeV. But you can see that when the proton becomes relativistic, when the proton energy becomes GeV, giga electron volt. In fact, there are now machines which are running at 1000 GeV. So at 1000 GeV, proton becomes relativistic, and you will find that you will have the high energy electromagnetic radiation emitted by protons. So only we are talking about the low energy at MeV range. protons and alpha particles, we don't talk about bremsstrahlung. But if you have relativistic protons and alpha particles, they will also emit bremsstrahlung. Now this bremsstrahlung, I see the spectrum, the energy. Bremsstrahlung is a continuous energy spectrum. So if you have electron of energy this much, then maximum energy of bremsstrahlung can be energy of the electron. But it is a continuous spectrum, and the average energy will be somewhere 1/3 of the maximum energy. So bremsstrahlung gives you a continuous spectrum with average energy 1/3 of the maximum energy of the fast electron. This is in fact a mechanism to produce gamma rays from electrons. These days, you can easily have high energy electron accelerators. So if you want to have an intense source of photons, you can use high energy electron sources and bombard them on high Z material like tantalum, and you can get, or tungsten, you can get electrons, the photons of all energy spectrum. Okay, so now, like we discussed the range of heavy charged particles, and what we saw that the heavy charged particles, the transmission graph, what I was showing here is the intensity of the initial electron is I0, it is passing through a thin slice of material, and the transmitted intensity is I, this is delta X, then I upon I0, that is called the transmitted intensity for fast electrons. If it is a monoenergetic electrons, like we have 1 MeV electron, then it will be just monotonically decreasing the intensity of this, because the electrons get lost from the path in the beginning itself, unlike in the case of alpha particles. For alpha particles, so we have like this. This is for alpha, or protons. For electrons, you will find electrons start getting lost from the path from the beginning itself, and that's why we cannot define, you don't have a well-defined range for fast electrons. So normally, there is no point doing an experiment to determine the range of electrons for monoenergetic electrons. But for beta particles, what happens? The beta particles, it has been found experimentally that the transmitted intensity follows an exponential decay. That is given by this expression I equal to I0 e raised to minus nx, where n is called the beta absorption coefficient, and this n, the coefficient, correlates well with the beta endpoint energy. What means endpoint energy? The maximum energy of beta particle. Now you know that the beta spectrum is a continuous spectrum. Why it is continuous spectrum? We discussed in the beta decay that because of the emission of three body interaction. So you have a electron, you have a neutrino, and you have the dotted nucleus. So the energy, the Q beta is shared in a infinite number of ways among the electron, neutrino, and the heavy residue, and therefore this continuous spectrum of beta is responsible for the exponential decay. So it does not have any phenomenological explanation why beta decay attenuation transmission graph shows an exponential decay. So what essentially happens is that the low energy part of the beta spectrum gives rise to the initial part of the exponential decay, and the later part, the high energy component of beta spectrum, gives you the later part. So it is a fictitious type of correlation. It doesn't have any particular basis based on a particular concept. But it became very handy in the earlier times, when we did not have the advanced detector systems. Then people are determining what you do. You take a source of beta and you put foils of different thickness, different foils, and you are measuring the loss in the intensity as a function of keep on putting different foils and what fraction is going out. So this is the experiment. This is the so many foils you put and you generate this graph. So I and I0. And what they found, this is an experimental finding, that the beta decay attenuation intensity is attenuated in an exponential fashion, and this attenuation factor absorption coefficient n, it has got an excellent correlation. And so from the n value, one could identify the endpoint energy. At that time, the radiochemistry people particularly, we did not have no access to high equipments. So you like a mass spectrometer. Now you can determine the energy spectrum by mass spectrometers. But so you want to find out the endpoint energy of beta, you just do a simple attenuation experiment like this one, and you can find out what is the energy of this beta. So beta counting, in fact, requires that you need to really take care of this attenuation. So if you have a thick absorber, for example, you are doing beta counting. How do you do beta counting? You have a sample on a plate, and you put this precipitate, and you put it in you have a detector. So beta will go from here to here, you detect the beta. Now, if this absorber material is having high Z material like lead or stainless steel or tantalum, then there will be backscattering. That is one, backscattering. And second is the self-absorption. So this precipitate will be absorbing, it will absorb. And third may be the radiative losses. So if it is a high Z material, brimstalling also can take place. So when you do beta counting, one has to be very careful not to use high Z backing material for beta. Okay, I did not discuss this part in the beginning as one of the dominant mode of interaction of fast electrons, because the energy lost by this mode is a very small fraction. So it does not really matter when it comes to loss of energy by electron, but it is a very fascinating topic to discuss. And in fact, it is also used in the detection of electrons. And this is called the Cherenkov radiation. Some people call it Cherenkov. I'll say we can use the term Cherenkov. So what is Cherenkov radiation? So the blue light that is emitted in a swimming pool type of reactor. So that is a particular manifestation of the Cherenkov radiation that is emitted, and the beta particle is passing through a dielectric medium. So what is Cherenkov radiation? When a charged particle passes through a transparent dielectric medium with velocity more than the phase velocity of light in that medium, then this charged particle emits electromagnetic radiation, which is in the UV visible range. So the energy of the photons that are coming out is very small. So a tiny fraction of the electron energy is utilized in Cherenkov radiation. But it is very interesting to see, even this one, if you put appropriate photomultiplier tube, you can detect the electrons energy, electrons intensity by means of this Cherenkov detector. So what exactly happens? What is the mechanism of this one? So what happens that, first of all, the condition for this Cherenkov radiation is that the velocity of electron has to be more than c by n. What is c? C is the speed of light, which is universal constant. N is the refractive index of the material through which the particle is passing through. Now, if you see the V by C, velocity of the electron upon C, velocity of light, called beta, then it becomes beta n has to be more than 1. So the condition for Cherenkov radiation is beta n is more than 1. Now, how can the beta n be more than 1? So velocity of the ion can be close to C at the most. Okay, so it cannot be more than C. The relativistic ion we just now saw, 1 MeV electron has the beta value 0.94, but it is not more than C. So if you have a medium of high refractive index like glass 1.5, there are certain materials, dielectric materials which are transparent and have the refractive index close to 1.5, then C upon 1.5. So the phase velocity of that light in that medium becomes much less than C. And therefore, velocity of the electron becomes higher than the phase velocity of light in that medium. And as the electron is moving, essentially the concept behind is that the electromagnetic field associated with the electron is moving in the direction, it has got electromagnetic field associated with that field, moves with velocity c by n. And so the electron is moving at much higher speed than the velocity of the field associated with it in that medium, and it is like, the field is left behind the electron itself, and so that field appears because of the field leaving behind the ion, it is emitting a core, and this condition is met for a very small time because the ion electron will finally lose energy in the medium, and the condition will be not met. So till that condition is met, which happens only in the high energy part of the beta, then you will find for that particular time in the initial phase of this it's a journey, it will emit that light, and that light happens to be in the blue region. That is why the Cherenkov radiation is having blue in blue range. So this is a typical swimming pool reactor Apsara U in Trombay, and you can see the beautiful blue color in the swimming pool. So any swimming pool type of reactor, if there is a fission has taken place, then the fission products are emitting beta particles of high energy, and you will see blue light. So Cherenkov radiation, in terms of energy loss, is not much, but it is important in terms of the beauty of the radiation and the detection of the beta by Cherenkov radiation. Lastly, I will discuss the interaction of positrons. Positrons are also anti-electrons. So in terms of collisional energy loss and radiation energy loss, they are similar to electrons. There is no difference, but there is a subtle difference between electrons and positrons. That these positrons, when they thermalize in the medium, the positron comes close to an electron and annihilates with an electron. So electron positron annihilate, and you get two. So the rest mass energy of electron positron is 1.022 MeV. That energy is now emitted in the form of photons. And since the electron and positron, as they thermalize the pair, momentum is 0, the two 511 keV photons are emitted at 180 degrees. So this is the positron annihilation, gives you two 511 keV gamma rays which are emitted at 180 degree. Why at 180 degree? Because the momentum is 0. When the positron is thermalized, its momentum is 0. Electron is assumed to be already stationary or very low energy. So at that time, when a system is annihilating, mass is converted into energy in terms of two photons. The two photons have to have 0 momentum, and that is possible when it is emitted at 180 degrees. In fact, there is another mechanism of 3 gamma emission. And when the 3 gamma emission happens, then they have to be of at 120 degrees each. So, but the 3 gamma probability is much smaller than the 2 gamma, and in fact, very rarely you see 3 gamma. So, the reason for the 2 photons to be emitted at 180 degrees because of the 0 momentum. And another very interesting aspect is the positronium atom formation. In fact, the positron and electron can form an atom like hydrogen atom, proton and electron, hydrogen atom, positron and electron, positronium atom. And the positronium atom has a beautiful chemistry. So there is a subject of positronium chemistry itself. And lastly, the positron emission tomography. The fact that the 2 photons are emitted at 180 degrees is utilized in detecting the tumors in the human body by injecting a positron emitter like fluorine 18, carbon 11, oxygen 15, and so on. So many positron emitters, when they are put into the body and they emit positron, the positron annihilate, give 2,511 keV gamma ray, and they can be used to detect the position of the tumors in the human body. So we have a lot of applications of this positron. I thought I will touch upon this aspect in this particular. So I'll stop here. Thank you very much. Next time I will discuss the gamma ray interaction. Thank you.